Welcome to Math 142. The first chapter we're talking about is chapter 5, and we'll start with 5.1 because that's where we start. We're looking at angles, and we need to talk about what they are and how we measure them. So we look at an angle, we say that it has an initial side and a terminal side, and we always measure the angle as it's rotating in that direction. So counterclockwise is considered a positive direction, and clockwise is considered negative, which is a little bit counterintuitive to me always, but that's how we've always measured angles. Okay. So we call where the angle starts its initial side, and then it rotates that side through some amount of a rotation, some amount of a circle, and wherever it ends is a terminal side. And we'd like to be able to measure how big this is. Okay. Just like you can measure length in different units, you can use feet or miles or meters or centimeters. There's more than one way to measure an angle. And the one we're most familiar with is degrees, but the other popular one is radians. There's a third one that's common if you're a geologist called gradians, and we won't worry about that right now. We'll start with degrees, and we'll look at radians later on. The farther you go in mathematics, the more powerful you'll find that radians are, and we hardly ever use degrees once you get past this class. Okay. So the standard position for an angle is to start here on a circle on this side. We call that 0 degrees, and then you let the angle rotate through. Okay. If I want to measure things in degrees, we say that there are 360, and we use this symbol right here for degrees in an entire circle. So if I want to find the measure of the angle shown right here, where this is an initial side and that is a terminal side, you could say that's basically 1/4 of a rotation. So it's 360 degrees divided by 4, which is 90 degrees. Let's look at something called coterminal angles. Okay. Two angles are coterminal if they end in the same spot. So if I start here and I let my sides rotate around an entire circle, I get to 360 degrees, and I can keep letting it rotate to this spot. And since it ends at the same spot as this angle, I would call this little angle of 90 degrees and the bigger angle, which goes around an entire rotation plus 90, so it's 360 plus 90 is 450 degrees, coterminal angles. 90 degrees and 450 degrees are coterminal. Okay. So I want to find an angle that's coterminal with 800 degrees, but I want my angle to be between 0 and 360 degrees, and that symbol right there is a Greek letter called theta. It's very common to label angles with Greek letters. Theta is one choice. Okay, my computer's wigging out. Alpha is another choice. This is the Greek letter alpha. Beta is a choice. Those are common ways to name angles. And another one is gamma. Okay. But we really like theta a lot for some reason. Okay. So I want some angle, theta. If you see a Greek letter, you can assume it's an angle in this class. But I want my angle to be between 0 and 360 degrees. But I want to have the same terminal side as 800 degrees. So one way to figure this out is to take 800 degrees and start subtracting entire circles. So that 90 degrees is coterminal with 450 because I can add on an entire circle and get back to the same spot. So I want to make my angle smaller in terms of how it's measured. Take that 800 degrees and knock it down to a more reasonable number. I can start subtracting off entire circles. If I take off 360 degrees, I will get 440. That's still a big ways around, so I'll take off 360 degrees again, and that will leave me with 80 degrees. And so I can tell you that 800 degrees is coterminal with 80 degrees. if I measured 80 degrees on my circle, this is 90 degrees from here to here, so 80 degrees is probably right about there. I can get to that same side, that same coterminal side, by going around one whole circle, another whole circle, plus 80 more. Okay. That spiral loop is the 800 degrees. Just from here to here is 80 degrees. Okay. So something's spinning around like a record or a CD or a tire. Those two angles are coterminal. Okay. Let's look at this one. Let's find negative 45 degrees on a unit circle and then find a positive angle that is coterminal to that. So if this is a unit circle right here or a circle right there, we said before that this direction is positive rotation, so I'm going to call that direction negative rotation. Negative 45 degrees is, let's see, here's 0 degrees. This is negative 90 degrees, that's 1/4 of a circle, so half of that must be right around there. That's negative 45 degrees. Okay. Spinning clockwise is negative. I want to find the angle that's positive but coterminal. So I want to go this direction and end up on the same spot. Okay. So since if I take this 45 degree angle and this big positive angle, it should add up to 360 degrees. I'll take negative 45 degrees and I will add to that an entire circle, and that will be 315 degrees. So two coterminal angles here are positive 315 degrees, which is coterminal with negative 45. So one of the things you'll do in your warm-up homework is estimate values of angles. And this picture here may help you. Well, it's a little bit hard to see on this screen. I can make it a little bigger for you. There's a nice one in your book. Okay. These are angles that show up a lot. We like them for a few different reasons. Okay. What's important to note is that if I look at the first quadrant, this is called quadrant 1. This is quadrant 2, rotating around in a positive direction. Here's quadrant 3 and quadrant 4. Okay. This angle is 30 degrees. Here's 45 degrees. There's 60, and then a quarter circle's 90. These angles here have symmetry to them. So this is 30 degrees. If I take 180 degrees and back up 30 degrees, I get to 150. 180 degrees, back up 45 degrees, I get to 135. So the 45 and the 135 and the 225 and the 315 are quartering those quadrants. Okay? And the 30, 60, and the 120 are splitting it up into thirds in each quadrant. Okay? This is a chart that may help you in the homework. It'll help you get familiar with it. It would be worth printing out that page in the textbook and just having that chart next to you, and we'll do the same thing in radians. Okay? It'd be actually awfully good for you to take this and label it yourself. It'd be very smart. Okay? So speaking of radians, let's talk about that. Okay? The 360 degree measurement, 360 is a strange number, and it comes from Babylonian times. They were very, very mathematical, and they used a base 60 number system, and that's why we have 60 seconds in a minute and 60 minutes in an hour. They did a lot of work with circles, so we also have 360 degrees in a circle. Okay? But it makes almost no sense to us when you think about it, except that we're very familiar with it, to have 360 degrees in a circle. It's a very strange thing to do. Okay? Radian measure is nicer because it's defined in terms of the geometry of the circle itself. Okay? And here's how that works. Okay? The arc length of a circle, or of a piece of a circle, is if you measure out some angle theta, that's a fancy script angle, theta, on a circle that has radius r, this distance along the outside circumference of the circle is the arc length. So this is a piece of the entire circumference. Okay. Now, for an entire circle, you know the circumference. The arc length for a whole circle is 2 pi r. At some point in your mathematical history, you have seen that equation. Okay? We want to find a portion of that. Okay? So literally, you can divide that big thing, 2 pi r, into whatever piece of a circle you have, and that's what the formula is going to be. Okay? So suppose I have a 45-degree angle. Okay. 45-degree angle is 1/8 of a whole circle, right? I can find the arc length for that, given some radius r. I'll leave it just as r, and I'll say that my arc length is going to be 1/8 of the entire thing. Okay. So it would be 1/4 times pi r. Okay. If I knew the radius was 3, then I could calculate that, and I'd be in good shape. Okay. The way they define radians, so that's not okay. Okay, that's great. We'll figure out a better formula for that for any angle in just a minute. The way they define radians is they said, okay, let's take a radius of a circle, any circle you want. Okay. I'm going to take a piece of string and measure the radius. I'm going to take that radius, I'm going to measure along the exact arc length that is the same length as the radius. So whatever the radius is here, that's also my arc length. So they took a piece of string, they laid it around the circle, and where that piece of string ended, they made an angle. Okay, 1 radian is that distance there. Okay, it's where the ratio of the arc length to the radius is 1. Okay. 2 radians then would be measuring over 2 radiuses along the outside edge of the circle. So I'd measure 1, 2, and I get right about there, say. Okay. It doesn't matter how big the circle is. When you do this, you get the same angle for a little circle or a big circle when you measure along the arc length the same distance as the radius. Okay. It turns out if I measured all the way around a circle, if I kept taking out radiuses and measuring here and doing it again and doing it again, I get about 3.14 times that I could do that to get to half a circle, and about 6.28 times around to the other side. Okay, that's pi and 2 pi. Okay. So a radian is defined to be is the angle where the arc length equals the radius. And in one circle, there are 2 pi radians. Technically, a radian is a ratio of length to length, arc length to radius. And since those are both lengths and you're dividing them, the radian is a unitless measure. When you talk about degrees, you have to use this little symbol up there, which is really hard to see. This is 330, and we use that symbol to denote degrees. Okay? With radians, you don't have to say that. You can just leave it blank, because the ratio divides out. Length divides by length. Okay? So in an entire circle, one rotation is 360 degrees, and it's the same thing as 2 pi radians. Okay. 1/2 of a rotation, which would be on a unit circle from here to there, would be 180 degrees, which would be pi radians. 360 divided by 2, right? 1/4 of a rotation, which would be to there. We found that to be 90 degrees, which is the same thing as pi over 2 radians. I want to find the radian measure of 1/3 of a full rotation. So first let's figure out what that is. Here's 1/2 a rotation. This is 1/4 a rotation right there. So 1/3 is right about here, I think. I could think of it as splitting up a pizza pie into 3 pieces. If I've got a whole circle, I want, starting here, that's about 1/3 of a rotation. Okay. To figure out what that angle is in radians, I would take a whole circle, a whole rotation, which is 2 pi, and I divide it by 3. So it's 2/3 pi. Okay. That's in radians. I can figure it out in degrees as well. In degrees, I take a whole circle, which is 360 degrees. I would divide it by 3, and that's 120 degrees. So this angle right here is 120 degrees, and it's the same thing as 2 pi over 3 radians. Okay. Since I know this stuff, I know that 360 degrees is the same thing as 2 pi radians. And I could write that if I divided both sides by 2. I could say 180 degrees is the same thing as pi radians. Okay. We want to be able to convert back and forth between radians and degrees. This is essentially a unit conversion. Actually, it's exactly a unit conversion. So I can use this, and I can write this as 2 different fractions. I can say that 180 degrees divided by pi radians, that's really 1, because it's the same thing. It's just in different units. It's like converting 12 inches into 1 foot. They're the same thing. Okay. I could also rewrite this the other way around and make it pi radians over 180 degrees. Those are the same thing. Okay. So if I want to convert radians into degrees, and I've got pi over 6 radians, okay, I want to multiply, just like I would with any other unit conversion, by something that's going to reduce out the radians and keep the degrees. So I would use this one, and I would have 180 degrees. It's the same thing as pi radians. Again, the radians don't really have to be there because they're unitless, but we write them down because it kind of helps us think. Okay? And then I can reduce that. Okay? I can reduce 6 into 180, and I'll get 30 pi. 30 degrees. I forgot the pi. I can reduce that too. Over pi. Now I'm happier. 30 degrees. That's my answer. Okay. What if I want to convert 150 or 15 degrees into radians? Start what you know. I've got 15 degrees. Okay. I know that 180 degrees is the same thing as pi radians. Half a circle equals half a circle. 2 pi's all the way around. So I want to get rid of degrees and keep radians. So I'm going to multiply this by 180 degrees. I can reduce the degrees out and keep the pi radians on top. 15 goes into 180 12 times. So I get pi over 12 radians. Okay. Radians I know are really uncomfortable at first. I promise you get used to them. But let's look at some common angles here so we can see it. Okay. I'll make this as big as I possibly can. Okay. They've built this circle so you can see where it comes from by taking an entire circle, and first they split it in half. This is 0 degrees. All the way around is the same thing as, or not degrees, it's also 0 radians. That's the same thing as 2 pi radians. Halfway around is pi. Then they split it, my artistic abilities are lacking, they split it in quarters. Okay. If this is pi, they just cut it in half and they got pi over 2. And then this is 3 pi over 2. Half a circle, half a circle, half a circle. Or sorry, quarter of a circle, quarter of a circle, quarter and quarter. Okay, okay, great. Then they cut that again. Okay. If that's pi over 2, this is pi over 4. This is the same thing. 1 pi over 4, 2 pi over 4. 2 pi over 4 is the same thing as pi over 2. So that means this one is 3 pi over 4. 4 pi over 4 is pi. 5 pi over 4 and 6 pi over 4. Okay. Now, I'm going to change colors here so you can see something. Okay. Instead of splitting up this into quarters, let's split it up into thirds. So you could almost pretend that this line here is not there. And let's look at taking that quarter circle and splitting it up into thirds. So I've got equal pieces here, here, and here. So I took pi over 2 and I split it up into 3 pieces. Pi over 2 divided by 3 is pi over 6 here. Okay. Here's 1 pi over 6. To get from here to here, I have 2 pi over 6, which is pi over 3. This is 3 pi over 6. Reduces the pi over 2. Here I have 4 pi over 6, which is the same thing as 2/3 pi. This one is 5 pi over 6. Here I have 6 pi over 6. That's just pi. Here I've got 7 pi over 6. 8 pi over 6 reduces to 4/3 pi. 9 pi over 6 reduces to 3/2 pi. This is 10 pi over 6, which reduces to 5/3 pi. And then this one is 11 pi over 6. And then I get 12 pi over 6. And I'm back home at 2 pi. Yeah. So let's find an angle beta. That's the Greek letter beta. That's coterminal with 19 pi over 4. 19 pi over 4 is kind of a pain in the neck to find. Okay. I'd like to make that a number that's more reasonable. So I want to find it that's coterminal with 19 pi over 4, but between 0 and 2 pi. One, instead of going around a lot of times, I'm going around sometimes. Okay. So 19 pi over 4. 4 goes into 19 4.75 times, right? So this is 4 entire circles plus 3/4 of a circle. Okay. So I'm just going to count this off. Here's 1 pi over 4, 2 pi over 4, 3 pi over 4, 4 pi over 4, 5 pi over 4, 6 pi over 4, oh no, sorry, 6 pi over 4, 7 pi over 4, 8, 9, 10, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. I am there. Okay. I'm sorry, it's 2 times around plus a little bit. Okay. 3/4 of a pi. Since the whole circle is 2 pi, okay, and this is 4.75 pi, okay, 2 pi around is 1 whole circle. I said 4, I should have said 2. Okay. I went around 2 pi, 4 pi, plus 3/4 more. I'm sorry about that. I keep waking out on one note here. Okay. This is where I'm at. So 19 pi over 4 is the same thing as 3 pi over 4. Those are coterminal angles. Okay. The way the book does it is they take 19 pi over 4 and they subtract 2 pi. So that means 19 pi over 4 minus 8 pi over 4 becomes 11 pi over 4. That's still too big. So they subtract 2 pi again, minus another 8 pi over 4. And that gives you 3 pi over 4. that meets the conditions of being between 0 and 2 pi, and so they're happy. Okay. I know all these pi's are strange things. You get used to it, and you need to get used to it. Radians are a much more convenient way of measuring things. The farther you go in mathematics, the more dependent we become upon them. Okay. Again, this circle is worth printing out and having, and it would be very wise for you to go and label this as 30 degrees next to the pi over 6 and 45 degrees next to the pi over 4, so you're used to seeing those things together. Okay. So we've figured out what radians are and what degrees are. We figured out how to convert back and forth between them. Let's go back and look at those arc length formulas again, okay, or make a better formula for that, and also for areas. Okay. Since radians are defined geometrically, a radian means something. It's the angle where the arc length equals the radius. It's very nice for formulas. Okay, so in these formulas, we've got a formula for arc length and a formula for area. In those formulas, you need to have your measure of your angle in radians. If it's in degrees, you need to convert it first and then calculate this. Okay, and OneMap will give it to you both ways. It'll have sometimes where they give you things in radians and sometimes in degrees. Okay, here you need to be in radians. Okay, the arc length of a circle is S equals R theta. Since the radian is defined as the angle where the arc length equals the radius, if the angle is 1, arc length equals radius. If the angle is 2, then you go 2 radians, and that's your arc length. So all you have to do is find the number of radians you have for your angle, times it by the radius, and you've got the arc length, because every radian is 1 arc length around the circle, okay? Or 1 radian around the circle. Radian, radius. There's a reason they match. Okay? So let's look at this problem. Mercury orbits the sun at a distance of about 36 million miles. In 1 Earth day, it completes 0.0114 rotation around the sun. If the orbit was perfectly circular, which it isn't quite, but it's pretty close for Mercury, what distance through space would Mercury travel in 1 Earth day? Okay. So first of all, I know I've got a formula, S equals R theta, because I just told you that. It was up there a little bit ago. Okay. There's my formula. Okay. My radius is 36 million miles, so I've got that. I'm just going to call it million. Okay. I need to find theta. Okay. Well, here's what I know. In an Earth day, it completes this much of an entire rotation. So that's a portion. That's not giving me the angle. I've got to figure out what angle I get if I go around this much of a circle. Okay. So to figure that out, I'm going to say an entire circle is 2 pi. Okay. And I am going a piece of that. 0.0114 of 2 pi. Does that seem reasonable? So this becomes about 0.0716 radians. That's my angle. I'm going to take this and plug R in for R, so 36 here, and 0.0716 in for theta, and I get 2.578, and that's million miles. That's the distance around the circle that it covers, from here to here, arc length. Okay. I can also find area of a sector. A sector is a piece of a circle here where I find the center of the circle, I measure out some angle, and this is my sector. I want to find that area. So here's my example. An automatic lawn sprinkler sprays a distance of 20 feet while rotating 30 degrees. What's the area of the sector of grass covered by the sprinkler? Okay. So if I have a circle, it starts there. 30 degrees is, that's 90. I want a third of that. That's about 30 degrees. Okay. I want to find this area. Okay. They've given me a formula. A equals 1/2 theta r squared. Okay. The way they figured this out is they know that the area of an entire circle is pi r squared, and I want a portion of it. So they took this and they converted it from the whole circle. They just figured out the fraction that you needed. Okay. The only problem I have is I have to have this in radians. 30 degrees is not in radians, so I need to figure this out. Okay. 30 degrees, here's 90 degrees. This is 0 degrees. Okay. 90 degrees was, let's see, 2 pi in a whole circle, pi in a half circle, so pi over 2 in a quarter circle, and I want 1/3 of that. 30 over 90 equals pi over something, and this reduces to 1/3. So this is pi over 3. That's my answer. Okay. So I know that 1/2 is just part of the formula. My angle theta is pi over 3, and my radius, they told me 20 feet. 20 squared. Okay. So I get pi over 6 times 400, because 2 times 3 is 6, and that multiplies to 104.72 square feet. Okay, so let's look at velocity. Okay. Velocity is how fast things move, and we're used to looking at miles per hour for cars or feet per second if you're running. We're good at that. Okay. But now we've got things that spin, and as they spin around, okay, there's an angular velocity as well. Some things can spin slowly and other things can spin quickly. The way you control how fast your car moves down the road is you control how fast the tires rotate. The faster that rotation happens, the faster you move down the road. That means two things. One, I can measure things this way. I can measure things that spin. I can count how often they spin in a minute, and that would be rotations per minute. I could measure that in full rotations. I could measure it in degrees per minute or degrees per second, and I can look at radians per minute or radians per second. Okay. Also, I can think about the fact that rotational velocity can be translated into linear velocity. Okay, so there'll be a connection between linear velocity and angular velocity, and we'll figure that out on the next page. Okay. Linear velocity, linear speed is like miles per hour or feet per second. You've seen before that distance equals rate times time. The velocity is like your rate. So if I want to solve that for r, the velocity, the rate, is the distance over time. S here is arc length per time. Angular velocity is going to be measured in something per minute. So it's rotations per minute or degrees per second. Okay. The units are going to be something over time. Per means divide. So rotations per minute is often abbreviated as RPM, like miles per hour is MPH. Rotations per minute is how many complete circles you get around in 1 minute. Okay. This is the formula. W stands for angular velocity. It's actually the Greek letter omega, equals the angle, theta, divided by the time, whatever the time unit is. Okay. So it says a water wheel completes a rotation every 5 seconds. Okay. What's the angular velocity in radians per second? So it says 1 rotation every 5 seconds. Angular velocity is the Greek letter omega, it looks like a W, is theta divided by time. My time is 5 seconds. Okay. I want to change this. I could write 1 rotation. That's an angular velocity. That works because it tells you how much it spins in a certain amount of time. Okay. But they want me to do it in radians. So I've got to figure out what 1 rotation is in radians. Well, 1 rotation is an entire circle. So that's 2 pi radians in 5 seconds. I could divide that and make this 0.4, because 2 divided by 5 is 0.4 pi per second. Okay. Now, they asked me for radians per second. I could also find the same thing in degrees per second. If it has 1 rotation in 5 seconds, I think, okay, they want not rotations per second. They want degrees per second. So how many degrees are there in one rotation? 360 degrees, because one rotation is a whole circle. Divided by 5 seconds. 5 goes into 360 sometimes, 72 times, I think, degrees per second. Okay. There you go. Now, since these equations have something in common, namely t, I could solve one of these for t and plug it into the other equation. There's a connection between angular velocity and linear velocity. If you're riding a bike and your tire spins around one whole rotation, unless your tires are skidding, you move down the road the circumference in that rotation, right? So if your tire spins all the way around once, you've actually moved, if you put string around this and cut that string of the circle and laid it out, you've moved that far in the same rotation. Unless your tires are skidding, that's what should happen. Okay? So I'm going to solve this for t. T times velocity equals arc length. T equals arc length over velocity. And I can plug that in here. Oh, maybe I'll write this way. T times omega equals theta. Time times angular velocity equals the angle. I'll put this s over v in for t. And then I will solve this. S omega equals theta times v. And then I happen to know that arc length is the same thing as r times theta. Need a little more space here. R times theta times omega equals theta times v, and that drops out. So I end up with r times omega equals v. Now, r stands for radius, omega stands for angular velocity, and v stands for linear velocity. It's kind of important to keep those things straight. Linear velocity, which is speed, angular velocity, and r is radius. We like that. Okay. So it tells me here a bicycle has wheels that are 28 inches in diameter. That means that r is 14 inches. That's important. A tachometer, which is just a means of measuring things, determines that the wheels are rotating at 180 rotations per minute. That's rotations per minute. That's angular velocity. RPM. Okay. Find the speed that the bicycle is traveling down the road. That is linear velocity. Okay, great. I need to figure out what all this is doing in terms of radians. So 180 rotations per minute is going to be 180 times 2 pi radians per minute. Since I use the arc length formula, when I substituted I said S equals R theta, I by default am thinking about radians now because I use arc length formula, and arc length formula only works well without some conversion factors if everything's in radians. Okay? So I'm stuck with this. Radians are really helpful, like it or not. Okay? So I end up here having 360 pi radians per minute. I want to know linear velocity. If they give you rotations per minute, that's angular velocity. So I'm going to say r times omega equals v. R is 14 inches because they told me. Omega is 360 pi radians per minute. Right. I need to multiply these together, which is going to be a big number, 5,040 pi inches per minute. That's what it is. It's a weird thing. You could convert it into miles per hour if you'd want to, but I'll spare you that conversation here in the video. Sweet. Okay, the last thing in the textbook is talking about minutes and seconds of a degree. Okay. Again, this is a Babylonian unit of measurement. So just like they took an hour and split it up into 60 minutes and split that up into 60 seconds, you could do the same thing with degrees. They didn't have decimals, I don't think. So if I find, and I'm not drawing this to scale, 1 degree, okay, it's a very small thing, but you might need a more precise measurement. So the Babylonians took that. I'm going to blow this up here. This is not to scale. They said, okay, that's 1 degree. They split it up into 60 pieces. That's one of them. And they said, I'm going to call this piece right here 1 minute. They write it this way, and it is 1/60th of a degree. Okay. And then they said, that might not be precise enough. So they took that and split it up into 60 pieces, and they make that 1 second. And 1 second, which is written this way, 1 with a double dash up there, is 1/60th of a minute. Okay. And it's the same thing as 1/3600th of a degree. Okay. So just like they take an hour and split it up into 60 minutes and split that up into 60 seconds, they take a degree, split it up into 60 minutes, split that up into 60 seconds. Okay. The book shows you how to convert things between degrees and radians, or not degrees, minutes, and seconds into decimal form. So, for example, if I have 1 degree and 60 minutes, well, not 60, that's kind of boring. Let's do 30, because I can think about that nicely in my head. 1 degree and 30 minutes. 30 minutes is the same thing as 1/2 of a degree, right? Because 30 out of 60 is 0.5. So I have 1.5 degrees. Those are the same thing. Okay. You can convert back and forth quite nicely, and the book shows you how to do it by hand. I'd prefer to do it with my calculator. Okay. So if I write down this angle, 19 degrees, 47 minutes, and 23 seconds, okay, I could also express that as just a decimal portion of a degree. Okay. The problem is this is base 60 and decimals are base 10. Okay. So I can convert this on my calculator by doing the following. Okay. Your calculator has built into it symbols for degree, symbols for minutes, and symbols for seconds. They aren't all in the same spot. The symbols for seconds is in green right above the plus sign, and we'll get there in a minute. The symbols for degrees and minutes are hidden under the angle menu. Okay. So if I want to get from 19 degrees, 47 minutes, and 23 seconds into decimal notation, I'm going to do this. I'll type in 19. I'm going to go to the angle menu, and since it's in blue, I have to push the blue button. The colors may be different on your calculator. And it says choice 1 is the degree symbol. Now it says 19 degrees. I need to add on to here 47 minutes. So go to 47. Back to the angle menu, and I choose choice 2, which makes it minutes. Then I want 23 seconds. Unfortunately, if I go to the angle menu, there's no seconds there. There's an R for radians, which is kind of nice, but there's no seconds. So to get to the seconds, I've got to, instead of this, go to, I need to back out of there, the alpha button, and above the plus sign it has seconds. Okay. That's the angle they gave me, but in decimal form it's this, 19.79. Okay, that's not so bad. Okay, that was good. Okay, so that's nice, but what if they gave me decimals and then they want me to change it into degrees and minutes and seconds? So what if they gave me 14.365 degrees and they want me to give this to them in degrees, minutes, and seconds? Okay. So I'll type in 14.365. I'll go to the angle menu. I'll type in degrees. I'm going to go back to the angle menu and see how it says this arrow, degrees, minutes, seconds. I'm going to push 4. And then it will give me That wasn't right. Let's try that again. 14.365. Oh, I think I'm in radian mode. That's better. Don't do the degrees to begin with. 14 degrees, 21 minutes and 54 seconds. 14 degrees, 21 minutes and 54 seconds. That should be a hash. Okay. Now, what if they tell me theta equals 3, and I want to change this into degrees, minutes, seconds? Notice how there's no degree symbol there? That means by default, this is in radians. And it means I need to change it first into degrees, and then I can use my calculator to figure out the degrees, minutes, seconds. Okay. So I first need to say, okay, 3 radians. Need to use a multiplying factor to change it from radians to degrees. I know that I want to have radians on the bottom because I want to reduce the radians out. And I know that pi radians is 180 degrees. Okay. So I get 3 times 180 over pi, which is 171.8873 radians. Okay. Then as my calculator, I'll type in 171.8873. I'll go to the angle menu. I don't use the degree symbol even though I really want to, but I ought not to because it doesn't work. And that will give me 171 degrees, 53 minutes, and 14.28 seconds. Okay, that's section 5.1. There's plenty to figure out on the first day of class.